All right. Today's paper is Starling from SIGMOD, and what Starling is a query execution engine that runs on serverless platforms. So what they try to do is they try to uh, come up with a way to run analytical workloads on function as a service platforms that usually have limits on the resources and also some timing constraints on how long execution can run on the platform. And their idea is to give the query latencies that are comparable to well-provisioned systems that are always running, but still reduce the cost. But give them in an ad hoc way, in a sense that only run executions when they are required on these uh, like per execution based platforms. And they also leverage the object storage services to store data. So in a sense that they don't have to depend on any provisioned infrastructure to run their queries. What Starling bases their advantages on three different properties. The first one is loading. Loading is when you have data in some proprietary internal format, or not just proprietary, but any internal format that the system needs to take advantage of in order to run queries efficiently and also at a high speed, for example. And if you look at, they also compare with a bunch of other existing systems that are out there. And many of them today don't require any loading. They are able to read directly from object service such as S3 and then run the queries for users. But there are like two notable exceptions, Snowflake and Redshift from Amazon that require some prescribed format for the data, like internal format for the data. And the second property they target is paying by the query, which not many systems today do. Starling does Starling's cost is per query. And similarly, there are other systems out there like BigQuery and Snowflake and Amazon's Athena that also charge per query. But the difference between Starling and all the other these other protocols is that we don't know that if they do internal provisioning or something like that. But for the end user, it appears that they charge by query. One exception is Snowflake, where the servers are provisioned, but it gives the ability for the users to shut them off. So that is why they also consider them as pay by query basis. And finally, the third property is tunable performance, which many of these existing solutions provide. What they mean by performance is having this cost to latency ratio. So if you want to pay extra cost for a low latency, you are able to do that, and vice versa. And Starling aims to provide all these three properties by taking advantage of cloud functions. Cloud functions are these cloud functions can be seen as some execution environments provided by cloud providers that have certain properties, like they have very low startup time. They can be started and stopped on when they are required. They don't have to be running all the time. And they also are built on invocation. So if you want to run like a 1-minute job, like you would be charged for that and how many times you invoke that job, for example. And they can read from cloud storage, and as as a data source. And most importantly, they can you can run thousands of these cloud functions at any given time. And when I mean thousands of workers, I want to point here specifically that they base this paper mostly on Amazon's services, because Amazon is the only one that offers invocation at large scale right now with their Amazon Lambda. They considered Azure and also Google Cloud, but they couldn't invoke so many workers at the same time, and they also had other constraints. In general, for these cloud functions, they are resource constrained containers, and they typically have like one core or and very less RAM, for example. And most importantly, you cannot communicate between functions. One container that is running cannot communicate with any other cloud function container. And but this is required for Starling to work because it's an analytical platform, analytics processing platform. And there are operations such as joins and shuffles that require these different functions to talk to each other. What Starling does is it provides a way to do this communication on top of cloud functions. So this is the overall working of Starling. There is a coordinator. You can run this coordinator must be always running. It can, but it is relatively lightweight, so it can be running in like a very small instance, for example. And what the Starling is, I want to is basically it's a query execution platform. Optimization or any query planning. So it takes some query that you have already planned and it executes them. So what the coordinator does is once it has a query plan, it spawns all the functions that are required. It makes calls to the Cloud Function service, and then it ensures that all these workers are spawned. And once a set of workers are done, it would basically go and execute another set of tasks. For example, one may be just processing from the doing table scans and doing some preliminary processing, and the next step could be doing shuffle and aggregation. So for each one of these processes, it will spawn a set of workers, wait for them to complete, and then spawn another set of workers until it finishes executing that query. And what this worker functions do is they do two things aside from computation locally. They read from cloud object storage, which contain the input files, for instance, and they then write intermediate outputs to some data platform, for example. They call this a communication medium, and they explore different communication mediums in the paper. And I'll also talk about them a little bit. And the other thing the workers do is once they are done, they have to notify the coordinator that they are done, or the coordinator somehow knows that the cloud functions are done. In Starling, they use AWS Lambda for Cloud Function Service. And for the base table, they use AWS S3, which is the Amazon's object storage platform. The base table storage can be the data in that Starling needs to process can be in any format, but what they have noted is the ORC format gives them better performance because it has certain metadata on top of each files that Starling can read and optimize, skip certain sections of the data from reading, so that can give them better performance rather than just reading plain CSV files, for example. Second, for intermediary state storage, this is the storage where when Starling spawns a set of preliminary workers, they produce some intermediate state, and this will be stored on the storage, and then this will be consumed by another set of tasks that, for example, do an shuffle operation, for example, or some aggregation operation. And for this, they analyzed different cloud service, cloud offering, different kinds of different ways that different kinds of services that the cloud offers, and one of them is Kinesis. I think Kinesis is, if I'm not wrong, I think it is a okay, Amazon SQS is the messaging service, but I forgot what Kinesis is. But
It was
the problem,
Kafka.
Kafka.
oh, okay, it's a Kafka. All right, yeah, I get it. All right, so Kinesis is Amazon's hosted Kafka service, which requires provisioning, and that was not useful for Sterling's purpose. And SQS is a queuing service, but the problem with that is they had very limited message size of 256 kilobits of messages. DynamoDB was good enough, but the problem was when they used them for shuffling operations, they had a very high cost to pay to DynamoDB. So what they eventually landed on was the S3 simple object storage service. And it had some features and also some challenges, but they overcame these challenges with Starling. The first property of S3 is that it's...
One question, Balaji.
Uh-huh.
So this intermediate storage is used only for shuffling, right? I mean, the reason we are using it is because the worker functions cannot do the shuffling. That's why some kind of intermediate storage is required. Is that...
Yes, they cannot communicate with each other for doing joins and shuffling and all those processes.
Got it. So therefore, they're implementing that kind of...
So yeah, they use an intermediate storage as a ad hoc solution.
Makes sense. Thanks.
Okay, so for that, for S3, it offers certain properties. The first one is write once. If you write an object with a certain key, you cannot update it. But what you can do is you can replace it though. And other features that S3 offers is cost per read, write, and unit of storage. So how they leverage, how Starling leverages that is it writes, every producer writes one single object so that they can only have to pay for one single write. They don't have to pay for multiple writes, even though they have to, even though there are multiple partitions to the data, which I'll talk about in a second, they just write one single object. The second thing S3's property is that it does not offer any read after write consistency properties. So for example, if you write to a key, it does not, you cannot read it immediately or immediately after the write. It may take a while before the write gets manifested in the read actually. And this has to do mostly with S3's tail latency problems. And so they overcome this by having writing to two keys, depending on if the first attempt succeeded or not. So they wait for a timeout. If the first attempt doesn't succeed, they just write to the second key. And this way, most of the time, they have a very good like they are able to minimize that tail latency from the S3 storage. The other property is atomic reads and writes. So you don't ever get partial reads while a write is in progress. So that is a good thing. You either get the write or you're able to read the last write, or you don't read anything. And another downside of S3 is high latency. S3 suffers from a very long tail latency, and they overcome this with, and also average high latency. So they overcome this with doing parallel reads. So they do not, the workers issue multiple reads in parallel, and for their benchmarks and also for their computation, it really works. And also to mitigate S3's read tail latency issues, they also issue multiple reads. So if they read, if they issue a read and it does not come back in time, they issue another read. And I'll talk about how they do that in the next slides. And on the right in the figure, what I'm showing is basically object, an intermediate state object produced by Starling after, let's say, after the first set of workers have completed. Uh, the orange part is basically the metadata, and the green part is the actual data. And the metadata holds information on different partitions that are in the data. And they also store the offset of these partitions. So whenever a read, whenever the consumer, whoever is consuming this intermediate object, when they do a read, they don't have to read from top to bottom of the whole object. They can read this metadata, skip to the offset they need, and then read the rest of the blob they want. And this gives two advantages. One is that for every read, you have to perform, for every reads you're trying to do, the consumer is trying to do, you have to perform two reads. One is reading a part of the metadata, and the second is reading the offset, moving to that offset and reading that partition, for example. And so this is how they basically used S3 as the intermediate storage. Going back, so they do query execution on the workers. And when they do query execution, they basically do three things. One is three kinds of workers at a very high level I'm talking about. One, they do base table scan and initial processing. And the next stage is they spawn a set of workers for doing shuffles and join, for taking care of the join operations. And finally, they have an aggregator to aggregate the results from the shuffle producers and give the final output. And when it comes to shuffle, traditionally, there is one standard way to do the shuffle, like I showed on the left of this figure. What the producers do is they produce partitions. They write to S3 for each producer. They write to S3 a single object, and these objects will have multiple partitions, as I showed in the previous slide. And what these consumers do is they only read the partition that they want, and from each of the producer's partitions. So for each consumer, they will read S partitions. And if you really, like what they say in the paper is that the number of reads will be 2 times S times R, which is S and R are the number of producers and consumers. But this this leads to very high cost for doing the shuffle operations if the number of workers are simply too high. And Starling needs many workers because the workers have limited memory. So, and also limited computing resources. So Starling has to, for many operations, deploy a massive number of workers in the scale of like 1,000 or 5,000. And because of that, they tend to produce many of these partitioned objects. And that would increase the number of reads for consumers, and that would cost more. So in order to overcome that cost, what they do is they trade the cost with some additional execution time. And they say that the additional execution time really pays off with respect to the amount of fewer reads they are doing right now. So on the right is the multi-stage shuffle operation they propose, where the idea is that for the producers still produce single partition objects as before, but now rather than having a set of consumers, you have a combiner operation in the middle where the combiner would only read from a subset of these partition objects and create an intermediate stage. And also, and they will produce an intermediate combined object into the S3 buckets. And then finally, the consumers would read this intermediate shuffle objects and then would produce the final output. And by doing this, they reduce the reduce the number of reads from a product to basically a sum. So now it is S divided by P plus R divided by F, where P and F are fractions. So each producer's reads decrease now by the number of partitions that you are able to do with the combiners. And then for each consumer, they only have to read a fraction of files produced by the combiner worker in the layer above. So this way, they trade execution time to cost, but at the same time, the cost of executing an additional layer is always cheaper than the cost of doing the reads from the S3 storage. That's what they found from the paper. Moving on, stragglers. So as I said, S3 has a long tail latency. So they mitigate it with basically doing multiple reads. And that is what they propose as the read optimization and the write optimization. RSM is basically read straggler mitigation. And on the left side, I show a plot that shows the completion time for some 256 KB reads to the S3 storage from the Lambda function service. And what they do with RSM is issue 2 reads. So they first issue the first read to the key. If the read is taking far too long, or if the key is not available because of read after write issues, with S3, they issue a second read with the second key after a given time. And what that gives them is this straggler mitigation, and they're able to curb the tail latency to very limited, to about like less than 50% of what they had without the read straggler mitigation optimization. And they also do write straggler mitigation, which is similar to read straggler mitigation, but they add an extra step. And so in this figure on the right, the blue is write straggler mitigation turned off, and the green is basically the same optimization as read straggler mitigation. But the orange is basically having a second timer and starting a second write request. So if a cloud function sends a write to an S3 bucket, it does two things. It first sends, what it does is basically it requests the write and then starts sending the data to the S3 bucket. And what S3 has to do is it has to basically give an acknowledgement that it has written. However, that acknowledgement can take a long time. So if that acknowledgement does not come, what they do is they start another write to a different key. And what they say is, and they don't start, so they start these two. So right now, these two writes are in parallel, and whichever comes first, they take the outcome of that operation, basically. They take that as the acknowledgement for the write. And these are basically all the different components of Starling. And I'll just, in the next few slides, I'll walk through a few evaluation figures that they have in the paper, and then we can talk about other figures too. I can share the paper and we can talk about other figures if somebody wants it to. So the first figure I have here is the performance or the cost of Starling itself. What they measure is how much does it cost to have Starling running for the whole day at a given query rate. What this evaluation compares is compares Starling, which is very ad hoc, to an always running solution like Redshift or Presto. And what they found is With Starling, the daily cost is very, very linear, because the more queries you execute, the amount, the cost you pay, and there is a relationship between queries and the daily cost. However, if you start for Redshift, because you provision, you always have to pay a set amount of cost. For 0 queries per hour, you already have to pay a minimum amount of cost. And while this does not, it may be too costly for smaller queries, if your average query rate is relatively higher, then Redshift really pays off. And this is the claim they make for Starling, is that they are really good for queries that come very rarely. For example, if the query is coming between 30 or 60 minutes, if the query duration or the frequency of the query is between 30 to 60 minutes, then Starling really pays off, is what their claim is. On the right is a similar figure, but in that they compare two other systems, Spectrum and Presto. Presto 4 and Presto 16 is a 4 worker deployment and 16 worker deployment, and Spectrum is Redshift, but with an additional optimization that is similar to Starling. It produces smaller workers, like Lambda workers, to read from the data stores and then perform computation on it. And similarly here, what they show is Presto is only least expensive in a given query range, given range where the average query is between like 130 and 140 queries per hour, but otherwise Starling is least expensive. So in this figure, they talk about the cost per query, and Starling's cost is constant for a given number of workers, and also the read operations. But what they also show is if the query frequency is higher, then other systems like Presto and Redshift, they cost higher. The cost per query would increase because now you have to provision more resources, and if there is any fluctuation, then you are still paying that cost. But for Starling, you're not paying that cost.
The graph said the otherwise, no? It's the query arrival time. So the fewer queries you have, the more waste you have in this other system. So the query cost becomes larger.
I didn't. Can you repeat that again?
The x-axis is not the number of queries; it's the time between the queries. Right?
Yes, correct.
So for other systems, like the 200 means you run less queries. So you just provision the resources and you're not using them. That's why the cost is higher.
Yes. Okay. Yep. I see your point. Okay. So what they are saying is, if you need to have certain throughput of queries to get your costs low. But if you have queries that are coming in rarely, if your throughput is low, then the systems, because of how you provision them, would have a higher cost per query. But Starling, given its nature, has a constant cost. Got it. Okay. And this figure I like. I put it here because this one showed the flexibility of Starling, given that you could choose the latency and cost trade-off, while in other systems it may not be readily possible. Like for Presto and Athena, they all have like a single cost latency trade-off, but Starling gives you that flexibility because you can choose to have more workers and increase your query cost at the expense of having a smaller latency, like at the benefit of having a smaller latency, or otherwise you could have you could trade that off with a smaller query latency, higher query latency with a smaller query cost. Yes, and finally, I wanted, this one shows all the optimizations and the latency benefits from those optimizations. The first one is no optimization for Starling, and the blue line is basically the latency provided by Presto with 16 workers. And if the biggest benefit comes from the parallel reads. The parallel reads are when workers not issue one read, but multiple reads at the time, because they take advantage of the throughput that S3 provides. And from there, the read straggler mitigation decreases the tail latency, and so does the write straggler mitigation. And finally, to really get to latencies below Presto, they have to, they depend on the double write, where they take care of read after write inconsistency issues. So they do a double write to 2 keys. And finally, they pipeline. I did not talk about pipelining, but what it really is if a certain set of workers have completed, they trigger the next stage of the process, like shuffling, while the other workers in the upper level are still doing computation. So it's like multiple layers are running at the same time concurrently. And that's all I have, basically. I can share other evaluation results if you want me to.